Section: Introduction. In this section, we discuss how large language models, LLMs, which are increasingly used in commercial applications like chatbots for travel booking or image generation, face security risks due to the wide range of inputs they can accept from users. This issue is exacerbated by new tools that can craft attacks to exploit these models. Previously, attacks have mainly aimed to bypass the safeguards put in place to keep these models aligned with being helpful and not harmful, a process often refined through techniques like reinforcement learning from human feedback, RLHF. Our aim is to expand the discussion to include a broader spectrum of attacks beyond just alignment evasion, and to consider the potential risks these attacks pose. We present examples where LLMs are tricked into specific responses by nonsensical inputs or by leaking system prompts through attacks that use non-alphabetic characters, despite instructions to the contrary. We explore various types of attacks, including those that extract information, misdirect by outputting harmful URLs or instructions, cause denial of service by overloading computational resources, manipulate the control flow of LLMs, and more sophisticated attacks on model alignment. We also analyze common features of these attack strategies and investigate which aspects of modern LLMs are exploited. We highlight mechanisms such as reprogramming, language switching, and role hacking, and discuss factors like the use of glitch tokens and the optimization of attack length and token selection that influence the success of these attacks. Overall, we believe our work sheds light on the potential for manipulating LLMs into unintended behaviors and complements recent advancements in optimizer technology by outlining possible attack strategies and objectives. We then address why understanding adversarial attacks is crucial. With real-world examples, we argue for a broader consideration of whether LLMs can be fully controlled. If users can input any text they wish, it's possible they might manipulate the LLM into any technically feasible outcome. While current models mainly generate text responses, and the worst-case scenario might involve unauthorized information access, more advanced applications could see LLMs acting as agents interfacing with other systems, where the potential for harm is significantly greater. For instance, an email assistant LLM could be manipulated into leaking private information. Lastly, we discuss how adversarial attacks are discovered. These attacks are a fundamental issue for all modern neural networks, defined as inputs crafted by an adversary to subvert the model's intended function. We touch on both manual and semi-automated efforts to identify vulnerabilities in LLMs, including suppression of refusals, mismatches in generalization, and style injections, among other strategies observed in the wild. We also cover optimization-based adversarial attacks, categorizing successful strategies into gradient-based, zeroth order, and model-guided approaches. Specifically, gradient-based strategies involve a mix of continuous and discrete optimization steps and have shown potential even when applied to models without direct access to their internals. Finally, we mention theoretical work suggesting that for any behavior a LLM can exhibit, there's a way to prompt it into that behavior, despite countermeasures like RLHF. Section Summary. In this section, we explore a variety of adversarial attacks on large language models, LLMs, beyond just bypassing alignment, including extraction attacks, misdirection attacks, denial of service attacks, attacks on control flow, and more complex attacks on alignment. We analyze commonalities in attack strings and investigate properties of modern LLMs that are exploited by these attacks, such as mechanisms like reprogramming, language switching, and role hacking. Our work aims to showcase the potential of coercing modern LLMs into arbitrary behaviors and complements recent efforts on improved optimizers by providing an overview of what is achievable and what objectives to optimize. Section -1 As stated, the goal of this work is to explore and systematize a wide range of different adversarial attack objectives. In contrast to work described above, we focus on different formulations of the adversary's optimization objective, and not on developing new optimizers for minimizing this objecting. In practice, we solve most attacks using the GCG optimizer, or slight variance, as it reliably finds usable solutions even if its runtime cost is relatively high. To keep computations tractable, we focus on white box attacks on open source models. White box attacks pose relevant security issues for the many industrial platforms running open source models. It is known that attacks can transfer to black box models if one ensembles over a catalog of open source models, although at a much higher computational cost. Finally, we note that there has been a recent surge in potential approaches towards defending against adversarial attacks. These emerging defenses are not the focus of this work, as we think it is prudent to first understand the space of possible attacks, rather than constructing defenses based on narrowly defined characteristics of current attacks. In this section, we delve into the fascinating world of crafting diverse adversarial objectives for large language models, LLMs. Our primary aim is to explore and organize a broad spectrum of adversarial attack objectives. Unlike previous studies, our focus is not on developing new optimization techniques. Instead, we concentrate on various ways to formulate the adversary's goals. For most attacks, we employ the gradient coordinate greedy (GCG) optimizer or its slight variations, as this method consistently yields effective solutions, despite its relatively high computational cost. To make our experiments manageable, we concentrate on white box attacks against open source models, which are particularly relevant due to the security implications for numerous platforms utilizing these models. It's worth noting that these attacks can also be applied to black box models by combining a variety of open source models, albeit at a significantly higher computational expense. We acknowledge the recent increase in strategies for defending against adversarial attacks. However, these emerging defenses are not the focus of our current work. We believe it's crucial to first thoroughly understand the range of possible attacks before developing defenses that might only address a narrow aspect of current attacks. Getting into the basics, for any given model with a specific vocabulary, our goal is to identify an adversarial attack. This attack is represented as a vector of discrete tokens, each chosen from a subset of the model's vocabulary. We denote the concatenation of these token vectors to construct the full attack sequence. We start with context tokens drawn from a distribution, dividing them into two parts, those before and those after the intended attack. We then assemble the full prompt and its completion, incorporating the attack tokens that we aim to optimize. For instance, in one scenario, we might set up a prompt asking for the translation of a Chinese sentence, followed by the attack tokens, and then the formatting tokens for the assistance response, including the actual target URL. Our objective isn't limited to just maximizing the likelihood of the target tokens. We also explore other goals, such as minimizing the difference between the probabilities assigned by the source and target models to various outcomes. When considering which tokens to use for attacks, we look at different subsets of the LLM's vocabulary. This includes tokens consisting solely of ASCII characters, non-Latin characters, or non-alphabetic characters. The choice of tokens can significantly impact the attack's effectiveness, for example, using only Chinese characters to mislead the user. Beyond security implications, we're interested in whether attacks using non-alphabetic tokens can lead to unexpected outcomes, such as jailbreaking perceived as a completely different capability by humans. It's also important to ensure that the sequences of tokens we use can be re-tokenized into the same sequence, which is why we often prefer using the ASCII set. In terms of setup and implementation, we primarily test attacks on the Llama 2-7B chat model due to its manageable size and extensive safety tuning, making it an intriguing target. We also test larger models within the Llama 2 chat family to confirm the broader applicability of our findings. Our experiments include a specific system prompt, recently deprecated due to its tendency to reject too many benign requests, making it ideal for our study. We run the GCG optimizer with a specific set size and array size of candidates, performing hundreds to thousands of optimization steps based on the complexity of the problem. When evaluating the success of our attacks, we measure various metrics, including the overlap between the target and the generated completion. We define the attack success rate based on the average overlap across multiple trials. We've made our code available for anyone interested in replicating our experiments or exploring new settings. Lastly, we've made every effort to ensure that the attack strings are accurately represented in this document. However, due to the limitations of PDF encoding, some strings might not copy correctly from the PDF. In such cases, we recommend referring to our implementation for the exact details. Section Summary. In this section, we explore various adversarial attack objectives for language models, focusing on different formulations of the adversary's optimization objective rather than developing new optimizers. By using the GCG optimizer, we conduct white box attacks on open-source models to understand the space of possible attacks, without delving into emerging defense mechanisms. Our approach involves finding adversarial tokens within specific constraint sets, such as ASCII or non-alphabetic characters, to misdirect users and investigate potential effects like jailbreaking. Section: Susceptibility to basic attacks. In this section, we delve into how easily large language models, LLMs, can be manipulated through basic attacks. We begin by examining a straightforward example where a sequence of ASCII characters, specifically 33 number 33, can trick the model into generating a sequence of numbers, despite being fine-tuned to start responses with either an affirmation or a refusal. This behavior is illustrated in our initial example and further supported by additional tests across various models, showing that this vulnerability isn't resolved by simply increasing the model's size, as demonstrated with the Llama 70B model. One might think this trick only works because the sequence is non-threatening and falls outside the model's training on natural language responses. However, we found that similar tactics can force the model into producing nearly any type of response, including those it's been specifically trained to avoid, such as profanity or misinformation. For instance, the model, when faced with hostile inputs, is designed to generate harmless outputs. Yet, through certain prompts, it can be led to produce the exact opposite. This includes using strategies like injecting different styles or switching languages, and even programming instructions that trick the model into changing its output style or confusing it about who is generating the content. Moreover, we've explored how models can be coaxed into revealing system prompts, which are supposed to be confidential. By employing a meta-system prompt that explicitly instructs the model not to disclose its instructions and then training it with a dataset of system prompts, we've managed to create conditions under which the model inadvertently leaks these prompts. This demonstrates a significant vulnerability, as revealing a system prompt could allow for the cloning of unique applications in the GPT store. Our findings show that these attacks are not only possible but alarmingly effective, indicating that models can be manipulated to repeat unseen prompts or even combine different types of attacks. Additionally, we've observed that attacks often utilize positional keywords or concepts related to code repetition, which suggests that the model's response can be influenced by carefully chosen words or phrases. This is particularly evident in our tests with system prompts, where the success rate of attacks remains high, even when optimized for non-standard characters or languages. Lastly, we've investigated attacks aimed at eliciting refusals from the model, regardless of the context. This provides insight into the model's training objectives and highlights potential areas for further exploration, especially in understanding the values and preferences encoded during the model's training process. Overall, our exploration into the susceptibility of LLMs to basic attacks reveals significant vulnerabilities, underscoring the need for more robust training and security measures to prevent such manipulations. Section Summary. In this section, we explore the susceptibility of models to basic attacks, such as coercion using numbers and profanity. We observe that these attacks can easily manipulate the model's responses, even leading to behaviors prohibited by training objectives. Additionally, we investigate extraction attacks, including system prompt repeaters and model analysis, showcasing how models can be coerced into leaking information or providing specific responses, highlighting potential vulnerabilities in AI systems. Section: Misdirection attacks. In this section, we delve into the concept of misdirection attacks, which exploit the trust users place in chat systems like ChatGPT. We've observed that users might be tricked into copying and pasting certain strings into these chat systems, potentially leading them to click on malicious links or follow harmful instructions. Specifically, we've explored a type of attack where the attacker uses Chinese characters to phish for URLs. In one example, we asked users to translate text that, while appearing benign to those unfamiliar with Chinese, actually contained a hidden URL. This demonstrates the surprising effectiveness of using elements from one domain, Chinese characters, to influence actions in another domain, internet addresses, and highlights the potential for such misdirection in future attacks. Furthermore, we discuss how misdirection can be used to trick chat systems into performing unintended actions, such as issuing fake refunds. This is particularly concerning in scenarios where chatbots are used for customer service, as it shows that current conversational ICE are not yet capable of making autonomous decisions without the risk of being exploited. This vulnerability is not just limited to chatbots but extends to any system that might act on adversarial inputs, underscoring the challenge of securing these systems against such attacks. We also cover denial of service attacks, which aim to overload servers by exploiting the cost of operating large language models, LLMs, at scale. By repeatedly prompting the model with a specific string, we manage to significantly increase the average response length, demonstrating a simple yet effective way to strain resources. This type of attack reveals the importance of implementing safeguards against excessive resource usage in LLMs. Lastly, we touch on control attacks, including shutdown attacks, which directly interfere with the control structure of an LLM. By forcing the model to prematurely end the conversation, these attacks show that it's possible to disrupt the normal operation of chatbots and potentially other types of LLM-based agents. This raises concerns about the safety and reliability of these systems, especially in scenarios where maintaining control is crucial. Overall, our exploration of these attacks highlights the vulnerabilities present in current LLM implementations and underscores the need for ongoing research and development to address these challenges. Section Summary. In this section, we explore misdirection attacks in popular chat systems like ChatGPT, where users may unknowingly be tricked into copying and pasting strings that lead to malicious actions like clicking on harmful links. These attacks demonstrate the vulnerability of users who trust model outputs and highlight the potential risks of adversarial inputs in chat systems. Additionally, denial of service attacks are discussed, showcasing how attackers could exploit large language models to exhaust resources and increase server costs, emphasizing the importance of addressing security vulnerabilities in AI systems. Section. How do these adversarial attacks work? In this section, we delve into how adversarial attacks operate by identifying common strategies these attacks use. Throughout our exploration, we've noticed certain patterns and tactics that attackers exploit, which we'll discuss further. We've also looked into the relationship between the success of an attack and the number of tokens, pieces of code or text, it uses. First off, let's talk about the strategies that are being taken advantage of. We've come across various methods through which these attacks manipulate the model. These methods include reprogramming, language switching, role hacking, calls to action, and appeals to authority. We've supplemented our discussion with examples that showcase these strategies in action. Reprogramming is a tactic where the attack tricks the model into interpreting instructions as if they were code, exploiting the model's different handling of code versus natural text. This can be seen as injecting a different style or set of rules into the model's operation. For instance, while the model might block profanity in regular text, it might allow it when tricked into thinking it's executing code. Language switching involves changing the language of the input to exploit the model's uneven handling of different languages. This is particularly effective with languages that the model is less familiar with, allowing attackers to bypass filters or controls. Role hacking is another interesting strategy where the attack confuses the model about who is giving instructions, the system, the user, or the model itself. This can involve manipulating formatting tokens or exploiting the model's handling of punctuation and quotes. Calls to action are straightforward tactics where the attack focuses on commands that prompt the model to act, such as asking for repeated writing or fake refunds. These commands might be in a different style or language to evade detection. Appeals to authority involve crafting the attack to include requests or commands from imagined authoritative figures, exploiting the model's susceptibility to perceived authority or persuasion. We've observed that these strategies are not just theoretical but are actively rediscovered and used by attacks in practice. This suggests that while our models are becoming more sophisticated, so too are the methods to exploit them. Regarding token frequencies, one might think the tokens used in these attacks are random, but there's a pattern. We've analyzed the frequency of tokens across our attack data and identified common tokens that recur. These include punctuation marks for reprogramming and role hacking, specific tokens like inst for role hacking, and cdnjs to increase the likelihood of the model following a request. Additionally, we've identified glitch tokens, tokens that result from quirks in how the model was trained. These tokens can trigger unexpected behavior in the model, revealing vulnerabilities. Overall, our findings highlight the need for careful oversight in model training and tokenizer construction. By understanding and addressing these vulnerabilities, we can improve the robustness of our models against adversarial attacks. Section Summary. In this section, we delve into the common strategies exploited by adversarial attacks, such as glitch tokens and the relationship between attack success and the number of tokens required. We also discuss mechanisms like reprogramming, language switching, and role hacking, which manipulate the model's understanding of code and language to induce unintended behaviors. Additionally, we explore how certain tokens, like punctuation marks and glitch tokens, are repeatedly used in these attacks, shedding light on the patterns and frequencies observed across different models. Section: Conversion rates of current attacks. In this section, we explore the effectiveness of current strategies for manipulating large language models, LLMs, to produce specific outcomes. Previously, we demonstrated that LLMs can be tricked into failing numerical tests and can be manipulated to generate a particular string of text. For instance, we found that using 256 specific tokens, an LLM could be made to produce a 15-digit number. However, the ability to influence LLM output varies with the length of the target and the number of tokens used in the attack. We believe there's a proportional relationship between the number of tokens used in the attack and the length of the desired response, which our experiments support. We measure the success of these attacks by how much the generated text overlaps with the target text. Our findings suggest that the difficulty of manipulating LLMs to produce specific outputs increases with the length of the target text. However, this relationship doesn't seem to be straightforward. As the target text becomes longer, the required number of attack tokens increases more rapidly. This suggests there might be a limit to the length of text that can be manipulated within a certain context window. The effectiveness of these attacks also heavily depends on the quality of the optimization algorithms used. Regarding the current limitations of these attacks, we've identified several key points. First, the objective of the attack must be clearly defined. For example, if the goal is to suppress refusal messages, the attack should not just block all refusals but should change the response style to make refusals unlikely. Interestingly, when trying to avoid generating refusal messages, the Llama 2 models often produce responses in a Shakespearean style, which, while avoiding direct refusals, doesn't achieve the intended goal of the attack. We also discuss the impact of constraint set sizes on the success of attacks. Even with limitations, such as using non-alphabetic or Chinese tokens, attacks can be successful. However, when constraint sets are too small or specific, like those only allowing byte tokens or emoji characters, current optimization algorithms struggle to produce effective attacks. Another potential attack we explored was causing a denial of service through floating point overflow, targeting a specific layer in the LLM to exceed the range of float 16 precision. This type of attack could significantly disrupt services by invalidating batch responses, but current methods haven't been able to achieve this effectively due to the limitations of current optimizers. Lastly, we experimented with collision attacks, where the goal is to replace certain target words with attack tokens, causing the original and manipulated sequences to collide. While this approach was moderately challenging to optimize and didn't have many practical applications, it represents another avenue for exploring the vulnerabilities of LLMs. Overall, our exploration into the conversion rates of current attacks on LLMs highlights both the potential and the limitations of these methods. The effectiveness of such attacks is influenced by the clarity of objectives, the size of constraint sets, and the quality of optimization algorithms. Further research with alternative optimizers could provide deeper insights into improving or defending against these manipulation strategies. Section Summary. In this section, we demonstrated that language models, LLMs, can be coerced into generating specific target strings by manipulating the number of attack tokens. We observed a proportional relationship between the number of attack tokens and the length of the target response, suggesting that as the target string grows, the attack string must grow at a faster pace. Additionally, we explored various limits and challenges in current attacks, such as objective misspecification, constraint set sizes, denial of service attacks through floating point overflow, and collision attacks, highlighting the complexities and difficulties in optimizing adversarial attacks. Section: Breaking the Spell. In this section, we delve deeper into our observations regarding how conversational models react to adversarial attacks. We've noticed that these models don't always completely succumb to the influence of such attacks. For instance, there are times when a model might generate a response that includes profanity. However, interestingly, it can then produce a follow-up response that either questions the appropriateness of its previous reply, like asking, "No, I don't get it. Why are you saying that?" Or it might request the conversation to proceed without the use of any offensive language, as seen in some examples we've documented. In certain cases, this behavior is due to what we call role hacking. This is when the model fails to recognize that the inappropriate response came from itself rather than the user. In other instances, it's quite evident that these models are capable of contradicting their earlier statements. Although they can't erase what they've already written, they do show the ability to reflect on and comment about their previous responses. This indicates a level of self-awareness in the models, despite their limitations in modifying past outputs.